Yes.
And that's quite common.
Yes.
How far away are we from having sort of automated ways of designing that?
So there's a lot of research into that right now. So it seems that machine learning scientists are really intent on making themselves obsolete. But like for these practical problems, I still chiefly trust my own intuition a lot more than an algorithm. The thing with these automated algorithms is that initially they'll know nothing and they'll make these really weird choices, and then you'll be training for 2 days only to find out that this is not really good. And so it's sort of wasteful initially. I think it'll be a while before we can, at least for these computer vision problems, until we can fully automate the process.
The time dealing with all these different rotated and repeated versions of your image that are, well, not repeated, they're modified and then refed to your system. Is there a way to tie the weights in your network together so that you don't have to do all this?
So that is exactly what we did in the second case. You can I present it as if I'm rotating the images. You can actually show that it's exactly equivalent to weight timing across 4 rotations. It's an implementation detail, basically. So this is actually all explained in the paper.
That does save you 4 to 1 of the computation.
It doesn't save you computation because you still have to compute the activations of the different. So the thing that matters is the relative orientation between the image and the filter, and you still have to compute it for all possible relative orientations. So it doesn't really save you computation. It mainly reduces the number of parameters, which is also good because that reduces overfitting.
So you used to improve the model, you use the training data, which you use the model, so test data, which you use the model to actually label the test data. So it appears that the model shouldn't learn anything from it because the model was used to train, to classify the data, and so how would you explain that it still gave some boosted?
So we treated this as basically a regularizer. So the nice thing is, once you have a bunch of trained models, you can generate predictions, average them together, so you can get, the best possible predictions you can get, and then you can use that to continue training. And this is basically a lot like distillation. I don't know if you're familiar with it. So you're basically saying that because when we do that, when we use these test labels, we're not actually using predicted labels. We're using the distributions as targets. So it's it gets a lot more information about what the probabilities should show.
So it's it was like feeding the information between different models. So you actually averaged before you used it for training, right?
So we had a bunch of models that were trained in a regular way.
Yeah.
We averaged their predictions together, did all our tricks to get really reliable predictions that would be ready for submitting to Kaggle, basically. And then we used those in our training batches. About 1/3 of our training batches would be test data with these labels instead of true training data. And this was a very strong regularizer. This allowed us to train networks that were twice as big.
So you do a lot with the data augmentation. Do you look at any generative methods for augmentation? So, for example, putting a plane to a galaxy, tilting it, regenerating images from it?
No. No. So I use mostly methods that are like. When I started, I didn't know anything about astronomy. I still don't really.
Yeah, I guess.
I just,
very much depends on the accuracy of your astronomical model.
Right.
So I liked your sensible use of normalization in the Galaxy example, where you considered the classifications and made sure that probabilities sum to 1. And that's a great idea. Did you also use that for the Plankton case?
Well, for the Plankton case, we just had to. It was a classification problem.
Yeah.
So we just had a soft maximum.
So there's no subclasses in there. You're not trying to
there's no hierarchy. But there is a hierarchy, but it wasn't part of the problem that we had.
Right.
So sort of ensuring that the model is rotationally invariant to the input. How about rotationally normalizing the input and training from that?
So those are two options that you have, and I think actually that not normalizing and just having a bigger model is better, because when you normalize, you're always going to make mistakes. And if you don't do this and let the model sort of handle this, the normalization sort of gets learned internally. And these models are basically much better at doing this than we are with a simple formula. So in general, I prefer to make the problem as complicated as possible and the networks as big as possible and let them handle it. What you could do is sort of normalize them and then maybe add a little bit of jitter back, so you still get this robustness against possible mistakes. That's another option.
I just wonder, a lot of your, a lot of Kaggle experiments use sort of human labels. And in many cases, we actually have errors in the labels.
Yeah.
Do you have a feel of what kind of contamination can you handle? I know it's a very difficult question, but as we keep on adding, for example, misclassified galaxies, probably some of them because people just make mistakes. You know, how robust is that in statistical terms? Can it handle 5%? Can it handle 10%? Do you have any view of that?
I think it's very problem dependent, but I think usually 5% will be fine. So in the Plankton case, we actually had these visualizations where we plotted both the loss, so the accuracy, the cross entropy, and the entropy of the model in a graph. And then you can sort of have each data point is a dot in this graph, and then you can sort of see where the model is very certain and wrong, and where the model is uncertain and wrong, or right. And when you look at the images where the model is very certain and it's wrong, then those are usually just mislabelings. So it's actually learning the correct thing, but it's getting punished for it because the labels are wrong. And actually the loss function in this competition, cross entropy, is super sensitive to this. So if you make a prediction and it's very wrong according to this loss, your loss can actually go up to infinity. If you're 100% certain, your loss will be infinity. So this is actually kind of an issue. Yep.
Right, so join me in thanking Sander again for a great talk and answering